So in this video we're going to introduce quadric surfaces. So here's the idea. We go back to pre-calc and we remember conic sections, and those were the different geometric shapes that we got when we cut a double napped cone with a plane. And the key is that conic sections had equations that were of this form: ax squared plus by squared plus cxy plus dx plus ey plus f equal to 0. And the idea is that we have second degree terms like x squared, y squared, and x times y. So this is all possible second degree terms you can make with variables x and y. And then we had all possible linear terms when we had conic sections that you can make using x and y. And then we had a constant term, which is your 0 degree term. So what's going to happen with quadric surfaces is we're going to take the ideas that we develop for conic sections, and we're going to extend it into three-dimensional space by adding in that z variable that we didn't have in two-dimensional space. So the general form of a quadric surface is going to be really analogous to the general equation for conic surfaces. We're going to have all possible second degree terms. So we have x squared, y squared, but now we add in a z squared term. And now instead of just an x times y as another second degree term, we have x times z and y times z, all possible products of two variables. And then we have all possible linear terms where we have just x, just y, and now just z. And we still have our constant term. So really what we're doing with quadric surfaces is we're taking and extending the idea of conics into three-dimensional space by adding in an additional variable. So in the reading that you have a complete explanation of the quadric surfaces and pictures of what they look like. So the only comments I would make that are in addition to what's there in the reading is to get you to really focus on the names. So with conic sections we had an ellipse, and you'll see what we do is we add the oid ending onto the names that you're already familiar with. So ellipse becomes ellipsoid. And what we have is if we take away the z coordinate, for example, we have x squared over a squared plus y squared over b squared equals 1, and that would be an ellipse in two-dimensional space. So all we're doing with an ellipsoid is adding in a z squared over c squared term. We're extending the idea of an ellipse into three-dimensional space. For a hyperbola, when you were introduced to hyperbolas in conic sections, usually that was introduced as a y squared over a squared minus x squared over b squared equals 1 kind of thing. So all we're doing now is extending and adding in the sum of the two minus the z squared over c squared term. And then what we want to notice is if we read carefully, it says the axis of the hyperboloid. So instead of a hyperbola, because we're in three-dimensional space, this will be a hyperboloid. The axis of the hyperboloid corresponds to the variable whose coefficient is negative. So this hyperboloid would be opening along the z-axis. And really what you want to identify from this is in your reading, you're not going to have been given all possible forms of a hyperboloid. So the idea is you get the sum of two squares minus another square, and we've got our constants involved. So we could have x squared over a squared plus z squared over c squared minus y squared over b squared equals 1, where the axis is opening on the or the hyperboloid is opening along the y-axis. Or we could have a y squared over b squared plus z squared over c squared, and the x squared is the thing that's being subtracted. X squared over a squared equals 1. So these little pieces in the reading, you want to read them carefully because they're identifying to you. So here's an elliptic paraboloid. So if we had just a single variable thing, we'd have a parabola. We're adding in a second y squared, we're adding in a second squared variable. The idea is that any one of these could be changed up. So for example, we could write x equals z squared over a squared plus y squared over b squared. We would still have an elliptic paraboloid, but it would be opening along a different axis. So they're going to, in your reading, you're going to get kind of something that epitomizes the quadric surface, and then we want to read this and then recognize that these can be modified and written in different forms depending on, for example, which variable is the linear variable or which variable is the one that's being subtracted. So those are just simple things to pay attention to. So I'm not going to go through quadric surfaces. I'm going to leave that to you in the reading. What I do want to do is go over how do you identify a quadric surface after you've done your reading. And the idea is quadric surfaces are going to come in this form right here. And what we're going to need to do to be able to put it in a recognizable form is complete the square on the general form of the quadric surface. So I would take something like this. I'm recognizing it's a quadric surface because the x is squared, the y is squared, the z is squared. So I've got the squared terms, I've got linear terms. So definitely a quadric surface. So how do we manipulate this into an interpretable form? And the tool is completing the square, and we complete the square on all three variables. So what we want to do is when we write this, we want to group the x's. So 9x squared minus 54x. And then we'll group the y's, so plus a y squared minus a 4y. And then we'll group the z's, so we have a minus 9z squared minus 54z. And this is all going to be equal to, I'm going to go ahead and subtract that 4 off of both sides. I'm going to get the constant term over on the right hand side out of my hair. And then because we want to complete the square, the leading coefficient on the squared terms needs to be a 1. So for these two, I'm going to need to factor off, in this first one I'm going to need to factor off a 9 to get a leading coefficient of 1 on the squared term. And 9 times 6 is 54, so it's going to leave me with an x squared minus 6 times x, and I'm going to leave some space here to complete the square with, plus I've got the y squared minus 4y sitting here, and down here I'm going to factor a minus 9 off. So minus 9 times z squared, and this would be plus a 6 times z. Leave some room for completing the square, equals that negative 4. And then you're ready to go through and complete the square. So I've got, because we've got the leading coefficient of 1, we can complete the square now. So we take the linear coefficient minus 6, we take half of that, which is minus 3, and then we square the minus 3 to get plus 9. And then what we want to recognize is we just added 9 times 9 is 81 to the left hand side, so we want to come over here and add 81 to the other side, so we're doing the same thing to both sides. Here are the linear coefficients in negative 4, so we take half of that as negative 2 and square it to get plus 4. I just added 4 to the left side, so I'm going to step over here and add 4 to the right hand side. And here's a 6 for my linear coefficients. I'm going to take half of that as 3, square it, and add 9. And I really have done negative 9 times 9 is negative 81. I just subtracted 81 from the left-hand side. So I want to subtract 81 from the right-hand side as well. Adding up the terms on the right-hand side gives us a 0. And then we completed the square on the left-hand side, so we can write it in the completed the square form. So what did we square for this? We squared a negative 3, so we're going to have x minus 3. It was a negative 3 that got squared to get the 9. Plus, here we squared a negative 2 to get the plus 4, so it's going to be y minus the 2 that was squared. And then it's going to be minus 9 times, and here we squared a plus 3, so it's going to be z plus 3. And then to get this into the form that we need, we're going to divide the coefficients out. So you divide everything by 9, everything by 9 on this side, everything by 9 on this side, so we get a 0. And we're going to wind up with an x minus 3 quantity squared plus y minus 2 squared over 9. We can really look at this as being a 1 squared if we want to, and the 9 we could look at as being a 3 squared. and then right here we're going to have minus, and this is a z plus 3 quantity squared all over a 1 squared. And then what we're going to do here is recognize that what we have is an elliptic cone. The reading is going to have things centered at the origin, and what we want to recognize is we can do function transformations to shift our quadric surfaces off of the origin. So I have an elliptic cone because I have the sum of two things being squared with a minus something that's being squared. So the sum of two things being squared minus the z term being squared here, so that it's an elliptic cone. This is an elliptic cone. And then the center of it's going to be given by the function transformation. So I have a function transformation. This cone shifted 3 to the right. So on the x-axis, the center will be shifted 3 to the right. On the y-axis, 2 to the positive direction on the y-axis. And here's a shift of 3 units in the negative direction on the z-axis. So I get -3 for the center. If we write this in the form minus a negative, as long as we have minuses everywhere, we can read these numbers off directly as the center of the quadric surface. So 3, 2, and -2 if we write it in that minus form. And again, this is just pre-calc, thinking about function transformations. Usually our quadric surfaces start at the origin. We can write them in a shifted form, and then it's our job, if we're looking to find the center of it, if the center is usually at the origin, how was the quadric surface shifted on the x-axis, on the y-axis, on the z-axis, by subtracting and adding numbers to the x, the y, the z variables. So this is an elliptic cone based on the form, but it's been shifted so that the center is at 3, 2, -3.